Hello everyone, welcome to the first Factry webinar on the topic, a data-driven approach to saving energy. Today we will have two presentations. One of our guest speaker, Gianni Vanneste, who has a track record on lots of energy improvement projects. So he will share with us his vision on how to tackle energy optimizations within your production facilities. And this will be followed by a talk by myself on how you can use data collection and data aggregation in order to support such an energy optimization process. So moving to the agenda of the webinar. So the introduction is what we are doing now. First there will be Gianni's talk, followed by mine, and we will have a Q&A afterwards. You can post your questions during the webinar in the chat of the webinar. They will be gathered and summarized by our colleague Frederick, who will then present the questions at the end of the webinar. So without further ado, I propose we move over to the first presentation. Gianni, maybe also introduce yourself shortly, and then you can take it away.
Okay, thank you, Jeroen. So I'm Gianni Vanneste. I work for Boortmalt as the Group Energy Optimization Manager. For those who don't know Boortmalt, we're the biggest malt producer in the world. We have 27 sites. Our headquarters is in Antwerp, and we are a very energy-intensive business. We use a lot of gas and heat and electricity, and it's a big part of our cost. So there's big potential in energy saving and decarbonization projects because this is the way we're going. Every company has to go to decarbonization of their plants. And this is my main focus, and this is also my passion. I've been working in this for my whole career, and this is probably the topic I will stay in for the rest of my life. So how to tackle an energy monitoring system and a time series database? Basically, in the end, a company wants to have the most efficient energy production of utilities, having the lowest cost of energy to produce their products, and also achieve carbon neutrality. But in order to achieve that, you have to have a solid foundation. And the energy monitoring system, the time series database, is crucial in that. You can clearly see that it's one of the most important things. Otherwise, you need also up-to-date PNIDs, you have to map your utilities, you have to have a lot of foundation in order to build the pillars. And the pillars are then based on the foundation. You can optimize your utilities and processes. You can do energy integration because you have all the data available to maybe combine cooling with heating to redesign utilities. You also have the tools then for good housekeeping to track your processes, to limit energy waste. And this foundation also gives you the tools to make reporting, data for management, for operators, for production managers, etc. So it's important to have this foundation in order to build a successful energy monitoring system and to achieve carbon neutrality and a low energy cost for your production. The why. This is one of the most important questions raised a lot by my kid as well, the why. But here there's a lot of whys, and the first one is good housekeeping. So you have to give the tools to your operators, to your managers, to track the energy consumption, to reduce waste as much as possible in order to put KPIs and follow up the energy consumption of your critical processes. Having these energy meters and these readings also give you an indication for preventive maintenance. Having higher energy consumption can also mean that you will have to do a maintenance and can prevent a shutdown eventually. Allocate correctly your energy cost. One product or one specific batch can be more costly. So it's important for your pricing of your products that if you go to marketing and sales, that you can clearly say for this batch or this product, you have to surcharge your client because the energy cost is a lot higher. It's very important in today's market as well for procurement of energy. It's very variable now. A lot is on the spot. So the better you can forecast your energy consumption, and a time series database with sufficient meters can give you the data to do better forecasting, which will result in a better procurement of energy. Shadow invoices, just checking if your invoices are correct with meters, that speaks for itself. And it's also a tool for design for new installations. So process and utilities. This data can give you insights for the correct capacity, but also for the redesign. It's not because it was always like that you just have to do copy paste. This data can be very valuable in the design of new projects in order to achieve carbon neutrality, for optimization of energy, etc. So what's important over here? So you have your primary energy vectors, which is electricity, gas, or any other fossil fuel and water. This goes to your factory. You have invoices for that, and then you're producing products. A lot of companies just have those invoices, and they cannot allocate these invoices correctly to their product groups or to their batches. In order to do that, you have to map your factory. Here it's seen as a black box, but you have to go in depth and map all your processes and utilities in order to allocate correctly your energy consumption to your batches or products. So how can you do that? So you have your primary energy vectors, gas, water, electricity. This is an example. Every plant is different. These can go directly to your processes. You have to map your process. It can be 12 processes, 15 processes. The site people know the process, your plant the best. And the most important one is the utilities. You need heating and you need different temperatures. So you will require steam. Maybe you need hot water. You will need cooling. You will have different cooling circuits. You will need compressed air. You have a wastewater treatment plant. Utilities are really important to map in a correct way and are also very important to track their efficiency. They are mostly the biggest energy consumers in your factory. So it's very important to track their efficiencies. And for example, for heating steam, you can map then the gas consumption versus how much heat you produce. For the cooling installation, you have the efficiency, the COP they call it, is how much cooling do I make and how much electricity do I put in the compressors. So all these ratios are important to track your efficiency. Then to correctly allocate your energy costs to your products, you will also have to allocate the consumption of your utilities to your processes, because your processes will require heat, cooling, compressed air. So to do the energy allocation correctly, you have to allocate that to your processes. And in the end, then you will have ratios. How much did process A use? Megawatt hour gas per ton of product, cubic water per ton of product, electricity per product, and so on. So this is key, analyzing your process, your utilities, in order to have a correct breakdown of your energy streams. This is an example. I could make 20 examples. It's a quite simple example. It's, for example, when you have a steam boiler. If you have a steam boiler, you will have gas going through it, which is the main consumer, it's the most costly consumer. You will have electricity and water. So you should install, of course, a gas meter, if possible, an electricity meter and a water meter. In the end, you will be producing steam. So you have to install a steam meter and a general steam meter. And then you have to install for each significant consumer, you should install also a steam meter. What does this information give us? So based on the first meters, so the gas, electricity, water, and what you produce by steam, steam is your output, you can have efficiency ratios. So tons of steam per megawatt hour of gas produced, cubics of water per ton of steam, etc. So you can track those, you can put KPIs. If they deviate, you have to explain them. And that's why you need even more data. Then you need specialists like an utility engineer or a technician to explain why these ratios deviated. And it can be several things. For example, you can track your flue gas temperature when it's too high. Maybe your economizer was not working properly. You can have the air temperature going to your combustion that is lower. So the important thing is that you will need a lot more data in order to explain why your efficiencies were deviating. If you have sufficient meters, you can also calculate the leakage. Because a steam network, you have condensate traps that can be leaking, you can have valves that be leaking, and when you trend this and you see a deviation, it must be that something is leaking or a condensate trap needs to be repaired, and this can be a huge cost for the company. Looking then at your int meters, so steam meters per process, Then you can, by allocating, you can allocate correctly your gas, electricity, and water consumption from the utility to the process to have a correct costing per product group per batch. So this all combined gives you data for good housekeeping, also for investments. It's not because you have a 20 megawatt boiler that you actually need it. So you could optimize your consumption, maybe make a hot water grid and a steam boiler, because maybe the majority of your processes need below 100 degrees, which gives opportunities for decarbonization, and also the correct cost allocation for each product group and batch. The key takeaways here, you will need a lot of meters, and these are key. If you don't have meters, you cannot build up an energy monitor system, and it's pointless to have a time series database. You will also need product information, volumes. The more data you have, the better you can also explain then the ratios. Before you start with the exercise, involve really key personnel in order to map your whole plant, your utilities, and your process. And this will also give you insights in where to place the meters, because these people will know this is a main consumer, this is a small consumer, don't consider it. So when installing meters, really focus on, start small and really focus on the big consumers. So have a phased approach. First we focus on the main meters, and then we go for the smaller consumers. Utilities, these are the key. It's the biggest energy consumption, and also most optimizations are possible there. So spend sufficient time on mapping the utilities. The tools have to be used. So when you install the meters, you have a time series database, the personnel has to be involved. So it's important that from the start of the project, you involve every layer of the organization, from shop floor to management. Especially the people on the shop floor, they will be following up the consumption, and they will have a lot of knowledge about the process. So please, my advice is involve them in the whole process, because it will give you a better end result. As already discussed, it has a lot of benefits having this. You can have the correct investments, and you can also maybe avoid investments, which is very important because you have the correct data. You have the tools, the data to optimize your utilities and your processes. You have better insights in your energy cost per batch, per product group, which then can be used for correct pricing of your end products. And also in today's market, forecasting of energy consumption becomes more and more important. So having the sufficient meters with a database can give you then the tools to do better forecasting.
All right, thank you, Gianni, for these insights. I think they will be very useful for our audience. In the next talk, I am going to give a practical approach on how you can use data to collect and process data in order to implement some of the strategies that were mentioned by Gianni. Also, a small reminder, if you have any questions for Gianni, please enter them in the chat, and we will handle them after the presentation. All right, a practical approach to saving energy. Personally, I don't know a lot about the different engineering techniques behind optimizing energy, but at Factry, we do know a lot about how to generate a data set that can support implementing such a strategy. So based on a few examples, I will try to give some learnings about that. Maybe shortly about Factry. We're a Belgian company founded in 2016, and we mainly focus on giving people access to data and insights from industrial processes, so they can use that data, for example, for energy optimization. We mainly develop two products: Factry Historian, which is focused on collecting raw data from the process and then processing that data to a useful form, and Factry OS, which is an MES system which can help guide operators and team leaders in the plant with information they need to actually do production. Think about planning, materials, and so on and so on. The techniques I will be discussing in this talk will be mainly focused on Factry Historian. Since our founding, we have deployed our solution basically all over the world. So we're present almost everywhere. A bit of context. So why do we give this webinar? Because we think the topic is very relevant in these days. As you know, there are a lot of high energy costs these days due to geopolitical factors. So there is a clear need for further optimization. But we do see that often the insights are lacking to drive these optimizations. So there is a lack of metering, people are recording stuff on paper, and so on and so on. So people know how to optimize processes, they just lack the data they need to do so. So we have some experience in giving people access to that data. So getting data to support a strategy can be seen in 3 different layers. So the foundation layer is, of course, the metering and the data capture from those meters. So without raw data coming from meters inside your process, basically the subsequent steps are not possible. So instrumentation of the process and accurate data collection from that process. Once you have that, you can start adding logic on top of that raw data. That means really taking the raw data and calculating some key parameters from it, like efficiencies and so on, and making these parameters visible within the organization so that people actually know what's going on around them and that they can, kind of easily consume this information and use it within their daily work. A third layer, once you have all the calculations, is, as Gianni also mentioned, is to correctly allocate energy uses to different parts of your process and different product ranges, for example, so that you know exactly for this production batch, I have used that amount of energy. For this range of products, my energy usage is higher than for another range of products. So each of these steps will be explained in a bit more detail during this talk. The first one, metering and data capture, in essence, is simple. You install meters, you start collecting data, and then you can visualize data coming from your process in function of time. For example, the amount of steam that was produced, the amount of gas that was consumed. We typically focus on using totalized values coming from the meters because a lot of the other data can be derived from such a totalizer. The benefit of using totalizers is that if you should have a gap of data collection, for example, someone has cut through a cable and the meter is not accessible by the data acquisition system, you still have the totalizer. So in your general energy consumption reports, you won't be missing any data. So how can we use Factry Historian to do that? It's very simple. We basically map measurements in a historian to sensors in the field. For example, in this screenshot, we have the total power consumption of a compressor. Depending on the setup you have in your plant, you can use different protocols to collect this data. Some meters are connected to PLC, so you can use OPCOA to collect the data from them. Some meters talk Modbus or BACnet, so different protocols are possible depending on the setup. Once you have that information, as I mentioned, we like using totalizers in this scenario, which is just an ever-increasing counter, counting the amount of energy or steam or gas that has been used. And you can use this information to derive additional data sets. So in this screenshot, we're looking at 3 times the same measurement, but in the top right corner, we have taken the derivative of this totalizer. So we transform it into an actual usage. And in the bottom right screenshot, we just took the start value and the end value of each day, and we just get an overview of energy usage per day. So this already, just this raw data gives you already a lot of detailed insights into your process. So what you get after this step, immediate transparency of the energy data, so people can actually see and explore this. So it can help create like a foundation and engagement within the workforce. And these simple graphs already provide valuable insights. So you can just create visualizations throughout the plant and then use also the data for root cause analysis in case you see a spike, for example, in a meter. You can use that data to dig deeper and see what actually went wrong. The second step, so the second layer I discussed earlier would be the calculation of key parameters. So raw data is one thing, but for example, for efficiencies, you would want to calculate, for example, how much gas was consumed per ton of steam produced, for example. In that case, I can do that afterwards. I can just collect this data and do this calculation, but then I don't have a real-time view on the data. So what I want to do in the historian system is to take this data and on a real-time basis, calculate this key parameter and then visualize it for the people who need it. So how do we do that? We create calculations. Calculations are kind of scripts that run on the incoming data and in real time process that data and write the result back to the historian. So you can use a derived metric from the raw data as a normal measurement and trend it across next to the raw data that was collected. Yeah, there's an extensive scripting language available, so you can, this is a very simple example, but you can use more complex logic as well, and then it is also calculated in real time. An example I want to give is from one of our customers, EISA in Chile. They operate biomass plants themselves, but they also give expert advice on how to optimize external biomass boilers. And one of the things they use with the data collected, so the efficiency of a biomass boiler is a bit more complex than a traditional gas plant, for example, mainly because of the variability in the input material. So biomass can, for example, have variadic humidity and so on and so on. So there are quite some complex formulas involved in calculating the actual efficiency of the boiler, like the thermal efficiency, chemical efficiency, and so on. There's a paper reference there, so you can do your own investigation if that would interest you. But the main concept here is that we just take these formulas and we transform them into a calculation in Historian. So we can actually, in real time, continuously calculate this efficiency and really closely monitor it in order to be able to react when it would drop, for example. The result, yeah, it's very largely visualized here now, but you get in one look, you see the current efficiency and how it evolves over time. And this is very valuable for the people in the plants because, yeah, it's real time. So as soon as something goes wrong, you can react and maybe avoid future problems compared to when you would only know the calculation, the efficiency from some Excel calculation of yesterday. So visualizing these key parameters that are derived from your data set is really important in terms of reaction time and follow-up of the process. So the benefits: more efficient and informed communication, identify problems before they become serious or while you still have time to react. And you can also use these KPIs, as they are logged historically as well, to follow up on potential improvements you have made. So if you've done improvement to the process, this should be visible in this KPI over time. A last step in this data-driven approach is the detailed energy allocation. So you can see here, again, an example. I have two measurements coming in. My energy consumed can be gas, can be steam, can be electricity. So basically an energy resource and a quantity of material that I have produced. This information is useful, but it doesn't allow me to ask a question. I don't know which product was active at which time, which recipe was active at which time, and so on and so on. So basically, I would need to add context to this information. So what we do for energy allocation is we detect when a certain batch is active, for example. I'm assuming a batch-based production process here. So when a batch is active and a certain product or product type is active on the line. And by identifying these discrete events within the production, we can then aggregate the data from the perspective of those events. So we take the raw data and we transform them into a data set that has this contextual information of the batch ID, the product ID, the energy used, and so on and so on. This allows me per batch, I'm now taking batch as an example, but it can be per shift or per day, whatever. to allow me to calculate key parameters that are relevant for comparison and reporting. In this case, I simply collect the amount of energy used per batch, the quantity that has been produced, and that allows me to calculate the energy per amount of material and also the cost per amount of material. Like Gianni already mentioned, instead of a generic energy cost, I can now directly associate an energy cost based on the type of product I am producing. How can we do that in Factory Historian? Well, I can add an event type for the entity I want to report energy on, in this case, a batch, but it can also be production shift or production week, for example. I define some properties on this event, like the energy consumption, quantity produced, and then I basically map those events on my asset tree, my hierarchy of the plant. So I can map my factory, I create the production lines, which of course reflect the real life scenario. And then I define how these events should be detected. For example, I can detect a batch based on certain parameters. If a machine is in a certain status and the speed of the steering is above a certain threshold, then I see that as the start of a batch and some other parameters for the end. So I detect these discrete periods and then I calculate my energy, my quantity, and so on top of that, which basically gives me the data I need to do energy allocation. An example here at one of our clients is Abrizo Jiffy. They make insulation material and protective packaging here in Belgium as well. And an example we've been setting up there is to calculate the energy used per batch as well. Now, one thing specific here is that they have a production hall with 2 production lines, 2 extruders, but they only have like the energy usage of the whole hall. So what we do is, by means of calculations, is to kind of create a virtual meter per production line, in which we kind of allocate a part of the total hull energy usage by using some kind of weight based on the power usage of certain equipments. So we kind of derive a ratio of energy use that is then associated to line 1 or line 2. So we basically create a virtual meter. You can see that in a lot of scenarios where not the whole process is instrumented with energy meters, that some energy meters are derived from the consumptions of other meters. In a second step, we modeled the plant and then created this batch event and calculated a lot of properties on those events. And then one of the properties is again kilowatt hour consumed, so the energy usage per batch. The result here, it's a little bit small, I realize this. So you have the production process, and you can see in the top table for each batch that has been produced. So each line represents a batch. We can perfectly see on which asset it was, what the batch ID was, which product was running, and also how much energy was consumed. If we then associate this also to the cost of the energy, we can very easily determine an actual energy cost per, in this case, cubic meter of produced material. We are using batch detection now. As I mentioned, you can at the same time, so simultaneously, also detect production shifts or other events within the plant and do these exact same calculations on top of that entity in order to have an as broad as possible reporting of your energy usage. So what are the benefits after applying this? Well, direct energy cost per product instead of a generic estimate across all products. You can compare the impact of different dimensions on the energy use. So for example, it could be that you produce the same product on 2 different or 3 different equipments in the factory. You can compare the energy usage by asset. So for example, maybe one asset is using more energy than the other 2. You can compare the impact of recipe parameters and also follow up potential improvements you made to those parameters over time. So if you see that a certain recipe is using more energy, you make some modifications. Now you can perfectly follow up for future productions whether or not this change had any effect. That brings us to the end of my story. So 3 steps from simple to more detailed in terms of processing data for energy allocation. The key takeaways I would like to summarize is, okay, build a solid data foundation that kind of speaks for itself, but don't do this exclusively for energy. Because if you really want to do allocation, you also need other data within the process, product IDs, recipe parameters. So basically, don't restrict yourself to just energy, because you need a lot more context than that. I think Gianni also mentioned this, work iteratively. It's not wise to do everything in one go, because you won't be able to find any nuances anymore. So work iteratively, create value at each step, and involve key people in the plant to create the necessary involvement and engagement so that they see the value of what is being done. And then third and last, go for open software and systems, because there is no one-size-fits-all solution or one product that is capable of doing everything. And in the future, we will need more and more data and software systems working together. So it's really important that if you invest in software, make sure it's easily integratable with other potential solutions towards the future. All right. Thank you for your attention. Before we move over to Q&A, I would like to point out that after this webinar, we will send you a survey requesting your feedback on the webinar and maybe some inspiration for topics we can cover in the next webinar. So it would be really good if you could give us your feedback on that. If all goes well, my colleague Frederick has been gathering questions from the chat. Frederick, are you there?
Yes, Jeroen, can you hear me?
Yes, loud and clear.
All right. The first question that we received is for Gianni. The question is, for data from 100 plus meters, so more than 100 meters, how do you manage to verify if those meters are working well?
Very good question. Well, if you start from scratch and you have to install the meters, I think you have to analyze very well which meters you install and look at the maintenance aspect of them. Like, there are no smart meters. It's actually a Profinet connection, for example, for flow meters or steam meters. And the meter already tells you if something is going wrong. So by choosing the right meters, it will already give you an indication if something goes wrong. Then there are, for example, temperature sensors. You can have temperature sensors you don't have to calibrate, and you have to have a calibration. So you have to also make a maintenance plan if certain meters need calibration after a certain time. When you have already meters installed and you want to verify meter, making balances is very important. So if you have a main meter and you have sub-meters, if the balance doesn't fit, it already gives you an indication, and the software can help to flag this. Then what you also can do, and the software can help, is that you know at a specific time, this meter should give this value, and the boundary condition should be, for example, +5 and -5. And when it's out that range, you could create an alarm or a warning to say it's out of this. So the software can also help. But when you start from scratch, really think about the meters you want to install and commission them correctly. And then as well, the software layer can also help you to flag when meters are not working. What Jeroen also mentioned is important. He uses totalizers, which is the correct approach, because it could also be that the data connection falls away. And when you have a totalizer, then it doesn't really matter. Then you can still integrate over time and you don't have data lost. If you would use actual values, then you would have a huge gap. So using totalizers could also help in this exercise.
Okay, thank you, Gianni. To the person that asked the question, if you want some more details, please add further questions in the box. A second question to Gianni as well. Do you have any practical use cases to share on using an energy monitoring system in the malt factory? And if so, what has been the gained efficiency?
So basically in the molds, the main consumption is in the kilning. So it's a drying process. And what we do with that, so we track the consumption of electricity and heat, and we have a certain time to finalize the process. We know the time we have, and depending on the outside conditions, we can actually steer the process to use less electricity or heat based on that. So yes, we track it, and we gained in energy efficiency. I know we're looking to roll that out in different sites. So that's we focus also on the main consumption we have, and in our process, that's the kilning. So the drying of our molds. So we focus on that because we can have the biggest benefits in that. It's also really important that it's integrated in the KPIs so that the sites have a KPI on heat consumption, electricity consumption. This is really crucial, and that's introduced in all our sites.
All right. Thank you, Gianni. A question for Jeroen. How do you deal with a continuous process where batches follow up one after the other? So the first batch is still ending while the second process has already started, and there's no meter for each separate machine that is used.
That's a good question, and kind of depends on the actual impact or the duration of the overlap. So usually when you have this kind of rolling changeover between batches, it is compared to the actual batch duration rather short. So you could argue that it's in that case negligible. In other cases, you would need to find a way to make your batches also overlapping. For example, by detecting actual activity on multiple locations within the line with separate meters, so that the start and end time of a batch, for example, let's take a filling line, for example, where you are still palletizing a certain batch while a new batch is already being produced at the start of your line, then you could argue that you want to separately detect events on the different equipments and not for the line as a whole, if the changeover time really is crucial or a big part of your different batches. Yeah.
All right, thank you, Jeroen. And another one for you. Could one also combine the calculated energy usage values with the current and maybe even the day ahead electricity prices in Factry Historian?
That would technically be possible, yes. Of course, additional data sources would need to be integrated so that you can actually combine them. But we have done that in the past, like incorporating price information, or even, maybe other factors that could influence your energy usage, like properties of the raw material that are detected only in a lab afterwards, so that we can integrate this other data sources with the energy data in order to provide more insights. So yes, you can connect external data sources, and day ahead prices and so on are a good example of that.
Okay, thanks. A general question, in a brownfield context, it is always hard to know which energy is consumed by which equipment. Is there a way to configure a metering plan in Factry for the measuring equipment, similar to the equipment model for the processing equipment?
Maybe that's a question for you, Gianni.
I think I highlighted it in one of my slides. So when you have a brownfield site, it's really important that you understand your asset tree and how all the energy streams are distributed. So you first have to really map this. And some brownfield sites, I know it don't have PNIDs, don't have any plans. So you have to start sometimes with it. So you will have to map it. And sometimes you can also put external measurement devices in order, before you buy the actual meter, to already map where the biggest flows are going, the biggest energy streams. So it's a big exercise ahead of installing the meters you have to do. And sometimes the exercise is bigger and takes more time than the actual installment of the meters and the connection of the meters.
Okay, that was the last question. So if there are no last minute questions coming in, that would be the end of the Q&A session. Yes.
Okay, thank you for following that up, Frederick. Okay, so what to expect next? To those of you who attended today and also others, you will receive the survey of the webinar and also a link to the recording that you can maybe share within the company if you think other people would be interested. And that is also valid for the key takeaways, which will be in a written form shared with you on Thursday. So also feel free to share these to other people who might be interested in. So the only thing remaining is to thank you for attending this webinar. I hope it was insightful in one way or another. And we look forward to welcoming you to a future webinar. Also, Gianni, thank you very much for sharing your expertise with us. And yeah, see you soon, everyone.
Thank you.